Good morning, I'm Bart. Since this is a very small workshop, maybe you can just go around the room and people introduce themselves. I mean, I think it's a nice thing to be small, then you can meet all the speakers and talk to everybody. And then maybe if we go ahead, we introduce ourselves, it helps also to the networking. So I'm Bart, I'm head of the research group COSIC, and I'll give a very high-level introduction. I assume many of you will be insulted by the level, but at least I want to set the stage and make sure that everybody is on the same page. Okay, so welcome everybody. And so I'll give a very brief introduction, well, an overview. Maybe some of you will find it boring if you can always start reading your mail, but it's like a high-level overview of where we are, because we're not sure everybody here is completely up to speed with things. And also try to give a little bit of a personal perspective on some topics. So I'll be very brief on cryptography. I guess the fact that you come here, you're probably aware of the quantum threat. Where we are with post-quantum and the migration. So I guess cryptography, we had mechanical devices in the 1920s, so about 100 years ago for wireless communication. And then commerce came in and we got electromechanical devices, including, of course, the famous Enigma. And then we got electronics involved, so people started putting things in chips, and IBM designed the DES algorithm for a chip. This was mostly for the finance sector. Then the telcos started doing stuff. Then Diffie and Hellman invented public key cryptography, but at that time it could not be implemented. In fact, even hardware was not capable of implementing RSA, and Professor Rivest tried for years and years to build an RSA chip, and he never succeeded. Just to give you an idea how hard it was in the 80s. But of course, communication systems did use cryptography, mostly symmetric. Then, of course, everything moved to software. Cryptography became implemented with software because computers were fast. And that, of course, meant that suddenly you got a boom from, say, 100,000 devices in the world to where we are today, which is something like 80 or 90 billion. So we got large-scale adoption, GSM system, the payment system, EMV, and of course, TLS, you'll hear more about it later. Then I think Snowden documents also had a very big influence in having end-to-end encryption really being deployed everywhere. Like in TLS, you could clearly see Let's Encrypt as a consequence of Snowden, and suddenly more than 90% of TLS traffic was encrypted. So we got mass adoption of messaging and end-to-end encryption in TLS. And of course now, well, the next challenge is PQC. That's kind of the history of cryptography in one slide, very briefly. So there is, in my estimate, something like 80 or 90 billion devices, applications, systems that use cryptography. And I will go very briefly over them. Most of them are not to protect Alice and Bob, as we teach in class, against bad Eve. Most of cryptography is there to take control over the users and for companies to make sure that they are in charge, or governments. I mean, a good example is your bank card. So people see that this bank card is something that protects their money. In fact, your bank card is a little spy that the bank puts in your wallet to make sure you don't spend more money than you have. And you actually don't even know what is in there. And if you travel, you'll find out that suddenly your bank card blocks because you made X offline payments, but you don't know what X is. Or the amount is Y, and there may be some formula in this card, but you don't even know what it is. It's there to check you. There is also the update system. Again, it's there to keep your devices safe, but you have no control over it. If there is 10 new features and you like 3 of them and you hate 7 of them, well, it's all or nothing. Either you don't update or you update. It's not really for you to decide what happens. It's there for the vendor to actually control the device and make sure that it does what they want it to do. Access cards. There is a whole DRM around gaming. It used to be, of course, now to Netflix, but it used to be devices like Blu-ray and DVD. Passports and identity cards is the same thing. It's the government deciding what is in there and what is happening there. So that's more or less the picture. There is also some cryptography to protect users. It's a bit less. It's our mobile phone system. This is the largest system. I think it's something like 9 billion devices, or among the largest one. It's not end-to-end encrypted. And of course, there is consequences. We're now in Greece. There was the Greek Vodafone scandal about 20 years ago, where more or less it was revealed that some entity, we still don't know which one because all evidence was destroyed, was eavesdropping on the prime minister, the mayor of Athens, the generals in the army, and so on, exploiting the fact that it's not end-to-end encrypted. Last year, Seoul Typhoon was leaked. So this is a very big Chinese program to hack all the telco providers in the US, but also in Europe, to get access to all phone conversations. One of the last executive orders of Biden was to tell US government employees to stop using phones, normal phone calls, to talk to each other about government business. So this is where we are in the phone system. We have cryptography, but we have no security. This is by design. There is, of course, the browser ecosystem. I will not say too much about it. It's the most successful one. There is now close to 600 million servers and probably something 10, 15 billion endpoints. Its cryptography is now fine. There is CLS 1.3. As we will see, there is also post-quantum cryptography there. But of course, the whole CA system still sucks. And more or less a corrupt government or can definitely issue false certificates. And this is a continuous battle. Also, the ADAS regulation kind of opened the door. Now it has been closed again, apparently. But there is a big fight there, not about the lower layers, but about the governance layer. Who can control this traffic? IoT devices also use this. I think what is really secure is the encryption on our phones. It's probably very hard to access, even by governments. The messaging is, in general, okay, it's end-to-end encrypted, but of course the metadata is leaked. WhatsApp has backup in the cloud. There is some issues with group messaging in WhatsApp and so on. So if you're really worried to use Signal, but of course Signal doesn't even show up, but this is only the 500 million to 1 billion thing. Signal is not that 500 million. So in some sense, I think as cryptographic community, we failed our users so far. We've done a lot, and the best we've done is TLS, and then the encryption on the mobile devices, and then things like Signal, but it's an uphill battle to even get everybody to adopt Signal. And without going too much in politics, more or less in the EU at least, the response is now, the debate currently is chat control again. We can talk about this in the break, but more or less governments want to check visual information and URLs before you send them and report you if you send things that they don't like. So even if you have end-to-end encryption, governments stop it. On the other hand, if you look, for example, at Russia, Putin there is now rolling out his own apps because he figures out that all these secure things, they're really dangerous for the state. And so there is actually still a big challenge to begun to just have the cryptography we have to make it secure, because in fact for end users it's still quite hard to be secure. I think that's the main message. It's an enormous success in some sense, because technology which was only available to 100,000 applications 30 years ago now is in everybody's pockets. But is it really secure? There is still many struggles to be had. Okay. And so 60 billion of this is public key cryptography. So biggest one is of course IoT, TLS, update system, WhatsApp, Signal, all the DRM systems, and then the EMV payment system. These are the biggest ones. I really like this graph because it shows the progress we've made from SSL, which was kind of, cobbled together by two smart people. So Netscape asked Paul Kocher and El Gamal to make a system to secure credit card numbers on the internet so people could sell dog food over the internet in '95. So it was a proprietary standard. SSL 2.0 was really bad. SSL 3.0 was kind of okay. But this slide gives a lot of information. It shows you what the best version supported is. So for example, here you see that after, I think, the Poodle attack, finally in 2014-15, the support for SSL 3.0 started dropping. And by the way, this is the top 150,000 websites. Okay? This is not the 600 million websites. This is the top of the top. Even there, most servers about 10 years ago still supported the old version of 95, which had many known flaws. Here you see the adoption curve of TLS 1.3. Here the one of 1.2. So in fact, in the beginning, there was no adoption whatsoever because nobody cared. And then Snowden gave it a push. So there is lots of information in there. You'll get the slide so you can stare at it. The main message is that this is easy to upgrade infrastructure to some sense because it's open source libraries, it's browsers. It's not the hardest to upgrade infrastructure. The hardest to upgrade infrastructure, I think, is all the bank terminals. They will be probably replaced by mobile phones because it's very hard to upgrade infrastructure. It takes 20 years to upgrade. But this is the easy to upgrade infrastructure, and that takes 10 years. That's the lessons to be learned. And maybe with some pressure, it can be done faster. And again, this is the top 150,000 websites. So you can still go to SSL Labs and look at stats. There is still websites supporting RSA 512 or SSL 3.0. They still exist. Okay, so that was the message and the quantum thread. Again, I'll go fast here, but so the first ideas of quantum computers were done by Riemann and Feynman in the early 80s. There was quite some experiments, I'll show them, but then Shor's algorithm came that showed factoring in discrete log. And the people claimed the first factoring in 15 in 2001. The first PQC conference was held in Leuven, so there were quite some efforts before, like Professor Buchmann in Darmstadt. Also, I had a PhD student working on these things, so there were people already in the 90s working on these things. And then IBM announced Condor, this kind of the biggest in terms of number of qubits announced last year. I guess I can be fast here, more or less. These quantum computers can do some things that other computers cannot, or can do it much faster by having entanglement and superposition. They cannot do everything. They can only run specific algorithms. But it turns out that factoring in discrete log, which is the 60 billion systems we rely on, are among those. Also, in the Snowden documents, it was revealed that the NSA spent 85 million on quantum computing in 2000. At that time, okay, this is at that time. So probably now their budget is more like $1 billion or so that you can just extrapolate. There is also this claim of McKinsey that China spent 14 billion, so there is always these studies that claim the others do more, so we have to do more as well. Then later on it was claimed to be 4 billion, so it's kind of, I mean, Europe has 1 billion euro agenda, the quantum agenda, of which about 200 million or so is wasted on QKD. But
this doesn't even contain what, like the other governments in the countries also additionally waste on QKD.
Yes. I think I didn't want to. I removed my QKD slides because I assume that this audience, most of people know that QKD is not what you should do. I mean, but Europe spends about 10 to 20 times more on QKD than on post-quantum, which I think is shocking. And it was just the shocking thing is not that this decision was made at some stage. The shocking thing is that it's clear to all the experts this is a waste and that nobody can stop it anymore. That's the shocking thing, I think, that there is no scientific mechanism or engineering mechanism or strategic level decision where we can say, oh, this is not good, we should change this. Yeah.
No, it is done on a strategic level by the EU. Yep. It is on purpose. I have talked to somebody from Deutsche Telekom recently who talked to BSI, and they said it's on purpose by the EU to spend money on quantum and QKD things and not on post-quantum crypto. There is a political reason for that.
Yeah, we can come back to that.
It's stupid, but it's, there's politics
okay.
there.
So I guess we're all here because of Shor, because otherwise we wouldn't care about these computers. And then you may have seen the breakthrough. I'll show you it also in a graph. So for RSA 2048, there was this guy from Google who made an estimate a while ago for 20 million physical qubits, not to get the logical qubits needed. So you need 2,000 logical qubits, or 4,000, sorry, for RSA 2048. There is different trade-offs. So people reduce the number of logical qubits, but then need more gates. So it's always complex. But so there was kind of a breakthrough in the spring of this year. So the estimate was reduced by a factor of more than 20. So more or less you need only a bit less than 1 million qubits to factor RSA 2048. Why is RSA 2048 important? Because it's in your credit card. It's in countries like Belgium, and I believe also Estonia, it's your identity cards. It's the EMV system. EMV system is the credit card system, which you do use when you make contact payments with your credit card. And my estimate is something like 6 to 7 billion cards and something like 50 million terminals, maybe 100 million. So upgrading that is a bit of a nightmare, and so this is still a widely used system. There is also Grover that reduces search to a square root. So more or less in cryptographic terms, symmetric keys have to be doubled in size. So this is why AES 128 also has an AES 256-bit version already since the 90s. So we kind of know how to deal with it, just make longer keys, and that's not too hard. And the other thing is that this algorithm actually is unimplementable because it's serial in nature. And I think for AES 128, people made estimates. I think they're like 2 to the 70 something qubits or gates you need. This is just daunting. And so, I mean, I also worked on this, and then if you work very hard with 4 people during a few months, then you can reduce it by a factor 2 or so, but it's like 2 to the 70 for those of you who don't know the order of magnitude, an Intel chip has something like 30 or 100 billion transistors. Okay, this is 2 to the 35 or something like this, 2 to the 36. This is what you put in a chip. Classical gates, okay, this we know how to make. Quantum gates are definitely more complex. How we ever going to build 2 to the 70, nobody knows. So in fact, the real scientific advice is ignore this Grover algorithm, don't double your key lengths, but it's just so easy to do that everybody does it. It gives you a good warm fuzzy feeling. Now use AES 256 and I can say quantum safe, and then you feel good. And who am I to say you shouldn't do it? It's not needed, but okay, do it. If you feel good about it, do it. And of course, it gives you some extra margin, so there is no problem with it. I like this slide because I borrowed it from Leuven van der Sijpen, who is the guy, is a student who was at KU Leuven, then went to Stanford. He factored 15 in 2001. And so he showed, which is not something so well known, that in the 90s, actually, there were quite some big labs working on quantum gates already. Because what people like to do is draw graphs about number of qubits, and then they always start somewhere in 2005 or so. But in fact, you should really see that it has taken more than 10 years to build a handful of qubits with a few gates. So I think that's an important message, that the development is already 35 years going, that people in physics try to build this stuff. And so we only got where we got with this 35 years of work. So here is their machine. It was a 7-bit computer, and they claimed to have factor 15. I don't know whether you saw the paper by Peter Gutmann on ePrint recently. More or less, he claims, and I think correctly, that more or less what they do is they build in the factors into the algorithm so that it will find 3 and 5. And so his argument is that this is more like a simple machine guessing a few bits, and you can as well have his dog bark a few times, and after a while you'll also come up with 3 barks, and then you found the factor. Gutmann makes a kind of joking article. One of my friends who's in physics sent me actually a Nature article from a few years ago that makes the same point. It had a very sarcastic title, but they were forced to replace it. And the title is now very neutral, but more or less people from physics making the same comment, that all these factorizations that you've seen actually are kind of bogus, in the sense that they would not work if you would be given a number without knowing the factors. The biggest change in quantum computing from the last few years is that quantum computers now get names. This is a major improvement. And why is this? Because companies are really spending real money, and then the marketing department gets involved. Everybody who works in a company knows this. If you spend lots of money, then the CEO asks, or the CFO, what is this money being spent on? And you have the marketing people then produce nice, cool press releases. And it's very hard to justify spending tens or hundreds of millions without having marketing press releases. And so this is why all these companies have to announce breakthroughs at least once a year, because if not, their budget will be cut. Okay, so this is a bit cynical view. Of course, they do make progress. But I think it's interesting observation that you have all these machines. So you may have heard or may not have heard of them. And so the biggest announced is Kookaburra. I don't know whether it's actually working. It's 4,000 qubits. But I think the one which probably can do the most is the Google one with only 100 qubits. But again, I'm not an expert in this. But the dimension is not only qubits, it's also error correction capabilities. So it's stability. So what is the error rate of your bits, and how long can you keep them? And then how are they connected? So it's actually like 4 or 5 dimensional parameter space. But journalists and press release people, they prefer to show qubits because it looks good and we can all keep the count. And so, for example, if you have 4,000 qubits, but they're much more noisy, then you're not closer to this 1 million than you are if you have 100 qubits, in fact, which are less noisy. So, but I think it's a reality of life that in the next decade, there will be every few months a big press release claiming a breakthrough. And then you'll have to really talk to the expert to find out, is there progress and is this meaningful or not? So IBM is famous for producing detailed roadmaps. Mike can tell you more about them, but I hear that they come from the marketing department. It's also interesting. I think I like that they do this because you can see what the plans are. What I recommend to do is look at the ones of successive years and see how they change. For example, one of the recent changes was that now the innovation roadmap was added. So there were things which were on the development roadmap, and now they're suddenly in the innovation roadmap. I don't have a good explanation for it. But it's nice that they have a plan at least, and you can see where they plan to go until 2033. But again, I cannot explain it to you, and probably you need to talk to an IBM expert for a day to understand really what is meant by this. But there is definitely investment, there is progress, and there is plans to get there. And my prediction is that next year there will be a different roadmap with slightly different numbers. And so it's just very difficult to predict. Google is actually, I like Google's roadmap. It's much simpler. It just says, you have go beyond classical 2019. So there was this debate with IBM whether or not they achieved quantum supremacy, but let's not go there. At least they could do cool stuff. Milestone 2 is 2 years ago. They actually were capable to have the first error-corrected quantum bit. So they have a single one logical qubit. So you don't need to be a genius to understand that if this is the first time this is claimed, that all the factoring algorithms must be bogus. Because to factor 15, you need at least 4 logical qubits, okay? Probably 8, 6, we can argue at least 4, okay? And people have been claiming to factor bigger numbers. But so if you had at 1 qubit, then you cannot have factored before 2023 unless... Okay. I think it's an interesting conclusion. So you get the same thing as those papers in a very simple way. Google puts no timeline. They just say the next step is a long-lived qubit, so because the one they built is short-lived. The next step is to make a gate. You also need that if you want to factor. You need multiple, and then the scale up. But the interesting thing is that they actually don't give you a schedule or they don't make promises. I mean, I hear that they're now getting closer to milestone 3, but I guess you'll have to wait for the press release. You can also look at the BSI report. So BSI publishes very long and detailed reports about all technologies. And so they look at all the technologies, and so they also identify basic functions, then the quality and the error correction. So they have all the stages you need to build a computer. Modulo the fact that nobody knows once you go to, say, hundreds of error-corrected qubits what the architecture will be, because you don't know exactly how the error correction will look like. But strange enough, based on this PSI, thinks it will take 16 years to build a cryptographically relevant computer. I don't know why they get 16 years from, but this is what the experts say. And then the people who then make recommendations come up with recommendations that are based on 14 years or so, or even less. And then also, if you read the statement, it's very careful and say, oh, and it could go faster in practice. So it seems that BSI really wants to push people in moving and being scared. Personally, I still think it may take longer, but we'll see. I really like this graph. So Sam Jack makes these plots where he has the number of qubits in the x-axis and the error rate in the y-axis. This is only 2 dimensions. As I said, there is more dimensions, but it's at least a good view. So more or less everything in gray has been realized. The blue thing is the error correction. So you need to have a certain error rate and size before you can do error correction. So we now entered that era in the last few years. So if you want to make money, okay, you can do quantum chemistry and you may not need error correction. And this is again completely beyond my expertise, but people spend now, or companies spend billions on this. But of course, if you can invent a new molecule or that can be used for coating or that can be used as a medicine, this of course you can make tens of billions, right? So this is probably what's going to be more likely applications is kind of exotic things in chemistry are more likely to happen, or they're closer by than some other things. So RSA is here. But then, of course, because of the breakthrough, this factor 20 this spring, this is the 2025, so these curves have now shifted to the left. But of course, there's still an enormous gap of orders of magnitude. And so this is what was achieved. So people think in 10 to 15 years, no, it was 35 years to get there. Of course, we don't know what the progress is. There is no such thing as Moore's law for quantum computers, where we can say, oh, it's happening with this rate. But the point I want to make is this gap is very, 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 very big. And this area took us 35 years. So then to say, oh, and in 10 years we'll go there, or 14 years, I find that very optimistic. But of course we don't know. You can ask the experts, and for example, the experts, this is what Michele Mosca does, the experts say that they believe that with about 26% probability, we'll get there in 10 years. Now you should be aware that all these experts are probably people who are building quantum computers and get big government grants or grants from their CEO, so they're not going to say it's not going to work. So I think that you have to take these experts with a large grain of salt, and even those experts, many actually think it will take more 15 to 20 years before they would bet 50 equal odds that they would get there. Okay. And then you can be Adi Shamir, and Adi Shamir says, well, I think at least 30 years. And this statement he made in 2023. So he doesn't believe he will still see it. I think Adi is about 70 years old, and he doesn't believe that it will happen. Of course, you can also say that Adi is biased because he doesn't want RSA to die. But I guess this is what we have as data. I guess this you've all seen, that's the Mosca equation, that what really matters is how long your data is confidential, because there is the harvest now, decrypt later problem. And then people, typically they put in 10 years as confidentiality. They take for migration, I took here 5 years, very optimistic. And then of course you can conclude that you have to migrate today. Why? Because, so we have our standards, you have to implement them, validate them, deploy them. If you can do this in 5 years, this is impressive. And then if the first computer is in 2040, then you're just on time to have 10 years confidentiality. And this is more or less the assumption that now all the government recommendations seem to take. So they assume 2040, which personally I think is optimistic. But then I think the governments have taken the attitude, we can't take the risk. Maybe it's not going to happen in 2040, but given what's at stake, we can't take the risk that it would happen by 2040. So it's a risk-based analysis. And it doesn't matter to them whether it's 2% or 5% or 70%. There is a risk it happens by 2040. So what is interesting, I think, if you look at government data, so I'm not an expert, but if you have classified information, typically it's 50 years. There is still some information of World War II that's not declassified. But like, for example, the SIGABA, the US encryption device used in World War II, was declassified in 1995, 50 years after World War II. So if you plug in 50 in this equation, then you should have started migration in 1990. I said this in a panel yesterday. So we are 40 years too late, because you should have migrated in 1990. the answer of Stefan from BSI was, well, but there was no Shor algorithm in 1990, so we couldn't have migrated. But I guess you get the point, right? I don't want to split hairs here, but if you have 50 years security, you should have used a post-quantum resistant system in 1990 to have 50 years security until 2040. So in that sense, all these predictions make no sense. If you have government data, you're already too late, and you should have migrated a long time ago. And what else is 50 years security? I think health data, like your DNA information, is probably highly sensitive for the rest of your life. And many of you may hope to live more than 50 years. I mean, not me, but it's kind of the range you're looking at. There is also like criminal records. They're now all being sent digitally. And there's a big debate, how long should you keep them? But so there is some information, in fact, where this 10 years is business security. Generally in business, people assume that after 10 years, things are public. There is a few trade secrets in the Coca-Cola formula and so on. But normally in a business, it's 10 years. But so I think it's important to see this, that there is this 50 years. And in that sense, you can also understand the panic in the government side, or panic, or let's say high level of urgency in the government side, because it's clear to them that even if this computer is only built in 2060, a lot of government secrets will be leaked, which was supposed to be still confidential. The good news is for signatures, this is zero, because if you re-sign everything the day before this computer is available, you're actually okay. It's a bit of a dangerous strategy, because, will you know when it's available and can you do everything in one day? But at least you have more time. And also, nobody believes that the computer will suddenly appear without people factoring first 10-digit numbers or something, or finding new molecules and making big press statements. But of course, you never know. So cryptographers started working on this problem already in the late 90s, and then there was a competition, the NIST competition, between 2016 and it says here 26, but we never know when it will end because the NIST competition seems to be ongoing forever. The main message for non-cryptographers is that if you ask cryptographers, please design us new systems that will give us 50-year or more security, then about half of them will be broken after 9 months. So this is not really a message of confidence in the general cryptographic community. So, of course, there is strong people and not so strong people, and there is optimistic people and not so optimistic people. But just be aware that you should not just follow the recommendations of a random cryptographer unless they're very reputed. And even well-known people can make mistakes. And this is the reason why this process takes 5 years. And then even then you should probably wait 5 years before you really trust it. This slide had lots of information, so what it shows is the number of schemes and then what happened after every round, so there were many rounds. And so more or less you see that the new ideas, 0 remained, there is hash-based signatures, there is no encryption there is multivariate, I think it's in a really bad shape, these schemes get broken and broken and broken. Code-based cryptography, well, as we'll see, there is now 1 standard candidate, or maybe 2 for some member states. And so all our eggs have shifted from number theory to lattices. So it's new mathematics, although it's not so new because the first public key system was, or one of the first was knapsack-based system. And in fact, lattices are not so different from knapsacks. But at least knapsacks in the 80s had a very bad fate. But they were of interest because, in fact, lattices are more efficient to implement, also knapsacks in the 80s, because they require only addition, not multiplication. And so they're actually more efficient. Just to show you, so COSIC, as you know, we designed the AES, and Johan Dahmen designed SHA-3, who was our student. So we actually had also a lattice scheme called Saber, based on learning with rounding. Instead of adding noise to your process, to your Gaussian system, we proposed to use rounding, which is the hardware people love because it's a lot cheaper to just round stuff. In fact, nobody could break the scheme, but somehow some people from the other camp could sow some doubt about these schemes. So they said, we can't trust this, we don't know exactly how it works, and is it secure? And so, of course, we were very unhappy that our scheme was not chosen, so we broke the other schemes. So more or less, so COSIC was isogeny-based, was seen as high potential. It was broken by Walter Kassel and Thomas de Cru, and then my student, Dwight Burlens, now at IBM, he broke Rainbow on a laptop over a weekend, and then this year he broke Supernova, another multivariate-based scheme, again on a laptop on a weekend. So we contribute, but now we are forced to contribute in a negative way.
How about PQC? I mean,
I will talk about it right away. Okay. So, sorry, I should move forward here. So the competition started in 2016, but already independent of it, IETF standardized 2 hash-based signatures, XMSS and LMS. So the Layton-Micali and Examet-Merkle signatures. They're actually schemes from the 70s, more or less, that use one-way functions to have signatures. They're very simple conceptually. XMSS and LMSS have a few optimizations. But the security is pretty straightforward. The problem is that they have quite large signatures, not super efficient. And LMSS and XMSS and LMS are stateful, which means as a signer, you have to keep state. You have to use your key bit by bit or part by part. And if you reuse a key, then you really compromise your security. So this is, for example, a very big problem in cloud environments where you have replication or you have virtual machines firing up at random when others have died. Then such a scheme is a nightmare. So if you know what you're doing, you have a reliable E-square problem, like in a smart card with a counter, and you're really sure that this counter will never repeat, then these schemes are fine. But if you have a laptop with some operating system that crashes all the time and gives you blue screens, it's very dangerous because you don't know after a crash, have I signed this message or not? And so you have a problem. So the competition, so 2 years ago, MLChem, MLDSA, so MLChem used to be called Kyber, and MLDSA used to be called Dilithium, so they had nice names, and now NIST has translated them into unrememberable and unpronounceable names. I don't know why. And Sphinx Plus is now called Stainless Digital Symmetry Algorithm, SLHDSA. I mean, it's the prize for the worst name ever. Not rememberable, not pronounceable. Why did they do this? But okay, Sphinx Plus is not the greatest name, but at least you can kind of remember it. And it is kind of cool, but it's what they did. So the standards were out, the drafts in 2024, and they were published in 2025, about a year ago. And then PhotoChem, this is lepsises with less structure. So less structure means that you have, I would say, weaker security assumptions, but of course bigger keys and bigger ciphertext. And so Germany and France like it. Germany seems to still like Macalise. So Macalise is a very old scheme, 1978. It has been modernized by a large team. And Macalise has huge public keys, but it has short ciphertext. So if you somehow an application where you can bake in public keys or transmit public keys in advance, in fact, the ciphertext are very small, which is actually a nice property for some applications. But France doesn't like it. The US doesn't like it. France doesn't like it. And then there was a paper at Eurocrypt showing that the Macalise matrix is not random, and you could distinguish it between the 260 something. And so some people say, so what? I mean, an RSA modulus is also not random. It's actually odd. So there is a debate, does this have a real implication or not? At least there is no key recovery or whatever. But so there is a bit of a debate about this. I think ISO will standardize all of them anyway. This is the prediction. Then there is also Falcon. So Falcon is a lattice-based signature scheme. It also get a horrible name, which I can't even remember. It will end with DSA, but it will be...
FNDSA.
What?
FNDSA.
Yeah, FNDSA, yes, fantastic. And then there is, more recently, also a new encryption scheme was added, HQC, which stands for Hamming quasi-cyclic. I don't know whether we'll change that into something
PQCSA.
Oh, fantastic. So in fact, the advice is if you don't want NIST to massacre your name, you should choose a name of 3 letters. That's what we learn for the future now. Okay. Okay. But so Falcon, I think, is an interesting case because it has shorter signatures, but it uses floating point arithmetic, so all the hardware engineers are horrified by it. There is just no way to implement it securely. And I'm not sure it will actually ever see the light of the day in the sense that... So the funny thing is about Falcon was selected and then, so this was after a 4-year competition, and then NIST said, we're not sure we actually know exactly how it works. They took it another year to actually standardize it, which doesn't give me very high confidence in security if that after 4 years you're still not sure you know how it works. But okay. There will be another signature scheme. Well, we'll show you a slide about this because NIST is not happy with the sizes. And then Japan is doing a competition. China is doing a competition. And one criterion to be in a Chinese competition is to not have a candidate in the US competition, which I think is very interesting. And then Korea is also doing a competition. So we go, I think, for public key, we'll end up more or less where block ciphers are, that every nation has their own block cipher. There is AES for most of the world, but then in SM4 in China, ARIA in Korea, Camellia in Japan. So we're going to have the same mess for public key, which I'm not sure is a win. It's a win for cryptographers because they have more schemes to break, but for implementers, I think it's a nightmare. So what's the bottom line? So for key agreement or encryption, key sizes in ciphertext are 3 to 15 times larger, which is for some applications a problem. But actually, so in RSA and elliptic curve, the key size is linear, but the computation is cubic. Except for RSA encryption and verification of signatures, there the verification or encryption is quadratic if you use a small exponent. So what happens in the lattice space is that the key size, well, everything is quadratic. The key size is quadratic, except for the secret key, but the public key is quadratic, and all computations are quadratic. So in fact, it's more efficient, potentially, than cubic. So encryption, you can never beat RSA with exponent 3 or 2 to the 16 plus 1, or you should use a 32 with exponent, it never really does, but that's another question. But so you can't beat RSA with short exponents. These applications will be hard to replace in terms of speed. Of course, if you have to transmit the bits, that's another issue. But even you're a lot faster than ECC, and the encryption is also fast. So in fact, these people say, oh, this public post-quantum cryptography is more expensive. No, actually it's cheaper. It's going to be faster, except for RSA with exponent 3, which actually you shouldn't be using anyway, because there are several papers showing you should not use exponent 3. And then for signatures, the problem is that the size of public key and signature, which is what you very often need to transmit, you sign something and you send the public key, is times 15 to times 30. And so this is a big problem for some applications, not for others. For signing code, it doesn't matter, right? If you sign 50 megabytes of code, it doesn't matter that your signature is a bit bigger, but for some others it is. Signing is faster and verification is comparable to faster. Again, nobody can beat RSA with exponent 3, which is what EMV is using today. This is the same thing in the graph. So you see the public key size. Here is Macaulay's. 1/4 of a megabyte. Ciphertext size to Macaulay's actually has very compact ciphertext. ECC is unbeatable. RSA is here, and then the structured lattices are here, and then PhotoChem will be a bit further, and completely unstructured lattices would be even worse. So it's kind of a trade-off, but we never get back to the same sizes as ECC. That's, well, the isogeny schemes, because there's a story which maybe is interesting to say or to tell you in one phrase. So isogenies are like mapping between elliptic curves, and they seem to be quantum resistant. They give rise to short keys, short ciphertext, short signatures, short everything, but then COSIC was badly broken. People thought this is dead. It turns out that the COSIC algorithm can be used to make new schemes. And now there is actually in Leuven this week, there is the isogeny week where all the isogeny experts, it's a very small group, but they're like all using all the whiteboards in our building to figure out new schemes. So, but there is some potential if these guys get their act together, and we probably wait another 5 years. We actually end up with smaller signature or smaller keys, but it will be on mathematics that you don't understand. Yes?
And that is currently has a runtime.
Yeah, exactly. And the time, I will show it, the time is terrible. So the sizes are small, but then the time is terrible.
The runtime of the sign is usually longer than the time it takes to come up with a new signature.
Yeah. Yeah. So here, this is what I wanted to show, this conundrum. So this is, I stole this from Wikipedia site or website, but I try to simplify it to the signature zoo. So you have here the security. So if it's red, it's not post-quantum secure. But it gives you the base of comparison. So ED25519 has 96 byte public key to signature, and it's about the same speed as dilithium. So MLDSA. And so MLDSA is 2,700 for this sum, and so this is the reference value. LMS, this is the state-based signature, is 1,100, is still above 1,000 bytes, and it's 5 times slower. Falcon, now you see why Falcon was chosen. It's a bit smaller than MLDSA, and it's also 2 times slower. But so there have been some improvements in some of the other schemes, but they still at like 5 kilobytes. Hawk seems to be a very good contender because it actually is comparable to Falcon and actually is faster than Falcon, and it's also lattice-based. So maybe we should drop Falcon and replace it by Hawk.
It has an extra social.
But it has an extra. You never get anything for free. So here is the isogeny. So you see this is the only one that can come close to elliptic curve, 241 bytes, but then you need is 9,000 times slower. And the multivariate, I took supernova as example. It turns out to be broken since I made the slide. And
Have a new version.
yeah, of course there will be a new version. But the point I want to make is that even the first version that was broken, that has the smallest sum, doesn't go below the kilobyte. And so what you see here, we come from 96 bytes, we've been really spoiled, and we have to pay a factor 10. I think this is, now also you also understand why NIST has extended the signature competition, because they're not happy with this, and they want to really go below a kilobyte. But it seems this is the open problem for the next decade for cryptographers. Find a post-quantum signature scheme with a few 100-byte signatures, and where you don't pay a factor 9,000 in performance, maybe only a factor 10 in performance. That's kind of the open problem. I think more or less I said most of the things. So implementers still are struggling with this lattice-based stuff. You make it post-quantum secure is okay, but then you have to make it side channel secure, fault attack secure, the floating point, the decryption failures, the noise sampling, the hardware people are struggling. And I guess the software people as well. For example, because this FO transform is used, the problem is if you have to decrypt, the first step is re-encryption, or after decryption you have to re-encrypt, which means you also have to have a side channel resistant version of encryption, which was not needed for elliptic curve and RSA. And this is, it seems like nothing, but of course it increases the cost a lot. So, but that's more the chess conference. I guess next week in Malaysia there will be a lot of talks about this, how to implement this in a side channel secure way. So migration started in 2023 already. You saw a first spike, and I think now the messaging apps have migrated. It's very easy because you just update the app and all the apps are updated. You can all be post-quantum secure. TLS, so I hope I don't steal your show, but Bas will tell you more about this. So Cloudflare has these nice graphs. And so 39% of the TLS as observed by Cloudflare, I don't know how representative that is for the rest of the internet, is already post-quantum secure, and Greece, amazingly, is close to 50%.
Yeah, it's because they have more Android instead of iOS.
Yeah, and so it was the same thing. The summer school of this project was in Bulgaria. There we were also over 50. I looked at Belgium, it's only 30%, so Belgium is not doing well. So of course we'll now move to hybrid cryptography. So people don't want to put all their eggs in one basket. So it's going to be hybrid. so RSA or ECC plus a post-quantum algorithm. And of course, you have to do the AND, because otherwise you don't have long-term security. What means the AND? It means you encrypt your key once with RSA or ECC and once with the post-quantum, or consecutive. So you need both to decrypt, which is a problem for migration. It means both sides have to be migrated. For signatures, you have a bit more flexibility. You can sign twice, and then you can hope the other side actually verifies both. What if they only check one? You actually have no way to check it. Right? But at least there, it's a bit less dramatic.
You have no way to know if they check signature.
Yeah, exactly. So in that sense, migration is easier. But of course, the problem is still that if you have to send a post-quantum signature, you have to send those 2 kilobytes. And even if they're not checked, you have to send them, and they will clog the whole system. And of course, eventually in 2040 or 2050 or whatever your favorite date is, we will just dump ECC because everybody will live in their basement a quantum computer and will factor numbers for breakfast. So then we can dump all this ECC stuff. So we have to migrate 60 billion libraries and devices and applications, or dump some of them. So what are the recommendations? Now we go to the policy. So the policy, so I think I'm still not sure this is going to happen really soon. And maybe it's interesting to look at the cryptocurrencies because they're actually betting on this, more or less, right? Because they decide whether they migrate or not. So there you can see there is real money at stake, and they can spend some of their money to be post-quantum secure. If they don't, it's clear that they bet that it's not going to happen. Of course, maybe they're good at cryptocurrencies and bad at cryptography, and they make wrong bets, but at least it's kind of a transparent betting market. If Bitcoin and Ethereum are not post-quantum, well, then they believe, at least a large number of wealthy people doesn't believe that something is moving, yes.
But that goes then back to what you earlier said, at least rely on signatures primarily and not on the
yes.
based on key exchange. So for them, upgrading is actually really fast.
Yeah, but of course the blockchain will explode, and maybe we can have discussions about this. Is for a subsequent talk, but I want to set the stage. I think the governments have decided they can't take the risk, and then I think so. They come with these dates. We'll discuss that. I think it's maybe interesting to understand this. So NSA, nobody understands what they do. So well, we're not surprised that they actually only have the highest security level. So they only go for level 5. So this is. But also they don't have Falcon in there. So I mean, this is the old slide before NIST had massacred the names. So you can still see what they're going to do without deciphering it. So more or less they said start in 2025, and then networking, browsers, and more or less you have to be done by 2030. And if I interpret this, you have to be done on 1st of January 2030. And then you get to 2033 for all the rest. That's what the NSA said. And again, they do many illegal things probably. They need 50 years of secrecy or more, otherwise they go to jail, because if you do illegal things and it leaks, you go to jail. At least in some countries you do. So they have an incentive to put a lot of pressure. Again, NSA says no hybrid. So NSA is going to dump RSA and ECC completely, which nobody understands, but that's what they do. I guess it's keep it simple principle. But they never really justified this. So either they have a very high confidence in post-quantum algorithms, or they believe that this hybrid thing is going to be such a mess that there will be more bugs in the software, in the checking, that it's actually better to not have the both. But they never justify this, why they think they should do this. So then NIST published a draft to which people can comment, and more or less this draft is very high level. It doesn't distinguish between applications, which is a bit surprising. It just says, if you use the low-level secure versions, like RSA 2048, you get time till 2030. And then for the higher versions, so 3072, 512 bits, so 128-bit security, you have time till 2035. Okay, so that's what they said, and you can comment on this, or you could comment on this. Then the White House said, this is as a consequence of the Seoul Typhoon attack in part, is they start securing your network finally, encrypt your email, use end-to-end encryption, so drop using normal phones, use TLS 1.3, and then migrate as soon as practicable. So this is Biden. So we were all waiting until the next executive order. And it came, it took a while, it took June, surprising, there were other priorities apparently. So more or less, a list of product categories will have to be released this December, so we're all looking forward to this. And then 1.3 has to be supported, but the support requirements in product solicitations has been removed. As soon as practicable has been removed, international collaboration has been removed. So this is a wake-up call for the EU. Before I continue, I forgot to say something about the signatures. I talked to some insiders in NIST, and there probably will also be a lightweight version of Sphinx. There is some debate about it. So Sphinx actually is quite big signatures, quite slow. It has 3 levels of indirection to actually get to the performance it gets. But that's because Sphinx, which is stateless, needs to be able to do 264 signatures and remain secure. Now, if you're doing code update and you need more than 2 to the 20 updates, you probably are doing something wrong in your software development process. So there may be applications where you only need a few thousand, a few 10,000 signatures, and then you could make Sphinx much more compact and much more efficient. And I think they're considering to use this. Of course, it's a risk, because then what you risk is that then some non-expert takes this version and then signs more messages with them than they should, and then of course you end up with a problem. On the other hand, if you're the automotive industry or the banking industry, I think you should know what you're doing, and you know that you're not going to send 17 million updates to your Tesla model, but only probably one every few weeks, and then you're probably okay with this. But this is still an item of debate. I don't know where they are, but this is, to me, seems like an obvious win to do, with all the risks, of course. You can never stop people from shooting in their own foot. So I guess they're doomed if they do and doomed if they don't, because if they don't do it, people will use LMS because it has more compact signatures, and then people will reuse.
I mean, there's at least one signature scheme still in the ongoing competition, which could be an alternative.
But still, it's good. So the EU, so running out of time, so let's go fast. So the EU actually has no crypto policy, because member states have always stopped having crypto policy. So more or less in the late 80s, the policy was the EU should not fund research on cryptography. In the late 90s, the policy was if the academic cryptographers get money, then the secret services get money too, but they don't have to publish. And then from 2014 to 2016, ENISA has published cryptographic algorithm recommendations, and then they were unpublished. At least the new versions were put on the website and then unpublished at the request of some member state, which I will not name in a meeting that's recorded. But you can talk to me in the break. But there was an event, an ESA-organized event yesterday, and it seems that now at least some member states that were blocking in the past are now understanding we need to do something. So, but about 1.5 years ago, the EU said we need a plan to make a plan. That was their decision. And then, interestingly, about 2 years ago, 18 member states, I think the group has now grown, said we have to do something. This is the same member states that have been stopping for decades the EU to do something. They now say do something, because there is this problem. Okay? And then they did something. So in April, for common criteria, there was this COSIC document was released. And it says FrodoChem, MLChem, it's fantastic. It's baffling me. It says RSA 2048 has to be phased out by the end of 2025. So you don't do anything for 10 years. And then in April you said, and by the way, until December you have time to remove RSA 2048. And then if you criticize this, you get very aggressive emails sent to you from BSI people, which I will not name. So I guess it's for new certifications, but still in Belgium there is like 5 or 6 million identity cards and a couple of million passports that all use RSA 2048. And I still think we will keep using them. And of course there is no public process. This is COSIC. The Bible comes down from COSIC, and those shall all do this, because we're in charge of common criteria. Then the NIST Cooperation Group also published a roadmap, which actually, it doesn't say much, but it says you have to categorize your applications by next year into low risk, medium risk, and high risk. The high risk have to be migrated by the end of 2030, medium risk by the end of 2035, and the low risk when you feel like it. That's more or less what it says. It says many other things, but there's nothing you can really disagree with. So my main analysis is that this is very pragmatic, and none of these dates is based on any science. I mean, the 2030 date is just, as I said, if you have a government application or medical data, you should have done it by 2015 or 1995 or whatever. So what is 2030 is the most realistic thing. If you shout at people now, maybe they can be done in 5 years, maybe. If you say 2029, people say we can't do it. So 2030 is like, okay, it's realistic, you can do it. And same thing with 2035. There is no scientific evidence. Even for medium risk, it's too late, but you know, it's like for most things you get 10 years and some things try to do it faster. So it's pragmatic advice and you can't be against it, but please don't claim it's based on science. It's just based on what can we do. You can say for signatures they could put 2040. I mean 30th of December 2040, because if they believe the calculator is there is 31st of January 2041, then, but of course if you do that then people don't do anything for the next 5 years. So I think it's good to understand that these dates we now converge on, and probably at some moment we'll shift them again if we can't get there, but at least it's a way to go to your management and get some budget to get something done, or to hammer down on people. Okay, that's more or less what I wanted to say as message. I'll skip the other details. I'll leave them to Mike. So it's definitely, depending on the application, it's going to be very hard. I see the biggest problem for PKI, where maybe you just have to design some new mechanisms, because what we have now with the current algorithms just doesn't scale very well. Okay, so signatures for secure boot and upgrade is urgent. TLS I showed you. And I think I will leave the rest for Mike and stop here. So more or less, we actually don't know whether this quantum computer will ever exist, but we can't take the risk. And governments have decided that we can't take the risk, so we'll have to go. Then people just didn't do nothing for a long time. I mean, the NSA were actually the first to make an official statement in 2015, and they said we will announce solutions soon. So soon is 7 years for the NSA, or 8 years. But so we'll have to make a risk-based approach. We'll, in the long run, have to make sure we can upgrade stuff faster, and maybe finally Europe will get their act together. So I'm optimistic that the messages are now going finally, at least the member states who were blocking stuff seem to be going in the right direction. Let's see. I mean, and like the SOGIS thing, again, maybe for some of you this is surprising, but we have common criteria since '95, and it has taken almost 30 years to decide that the common criteria are common among EU members. But at least the message is they have now decided it. Okay, so I'm going to stop here. Thank you for your attention, and I'll hand over to the next speaker. Thank you very much.